Starts Tamal.
Hello.
Yes, you can start, Saikat.
Okay. Okay. Yeah. 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 Okay. So, hello. Yeah. Myself, Tomal and Shoikat. So, yeah, the key of this course for the analog electronics. So, we can start the course as there is no one. So, let me start with some basic concepts. Shoikat, can you please uh, you can introduce yourself at the very beginning.
Switch on the video mode.
Hello.
Switch on the video mode.
Okay, but we don't have the webcam. Just a minute. Just a minute. Yeah. Am I audible? And am I visible?
Yes, yes.
Okay. So, yeah. So this is Tomal, and actually we have only one webcam. So I'm just sharing from Shoikat's desk. So he's also here. So Shoikat, can you please come once?
Hello, myself Soikat Das. I am research scholar at IIT Kharagpur. Here with us Tamal sir. He is the senior research scholar at IIT Kharagpur. So uh, no one is here. So
We'll start
it
with some
is
basic
basic concept. So Tamal will start.
Yeah. Yeah. So I'm just starting the session now. Okay, so as there is no questions at all, so I can start from some basic concepts. So one of the main thing is that first of all, am I audible? Just for final confirmation, Shaikat, can you please check once whether am I audible or not? Am I audible, Shaikat? Hello, hello. Am I audible?
Yes, yes, yes. You are audible.
Oh, okay, fine. So let me start with some basic discussions. So first we will go with some basic circuits related thing. So the very beginning, whatever inserts course, probably you have might seen that the use of analog electronics is such as suppose you have the you are sensing some antenna signal. Sorry, I'm very first time using this pen tab, so it is a little bit problematic for the first time. So suppose we have some sensors, and the sensors are sensing some maybe some temperature it can sense, or maybe some concentration of any material or anything. So once those are sensed, so what we normally know that we have in our home, we have some digital thermometers, or we have some gas sensors which is showing the digital readings. But mostly those are sensing the analog signals. So those analog signals, we need to first process the analog signals. Sorry, we first need to process the analog signals, and then we need to use the signal acquisition circuits. Something it's called signal acquisition front end. Signal acquisition front end circuits, and then we just convert those things using some analog to digital converters. So the basic flow chain of any analog system is something like that. We have some sensor. We have some sensor, and that sensor is sensing nothing but some analog signal. But two things you need to worry, that why we are not adding the ADC directly here. So normally what happens, that if we add the ADC directly here, then this signal, this whatever the sense, whatever we sense from the directly from the environment, that is analog in nature, and it contains the signal. It is we are representing with S, and also the noise we are representing with small n. So we have to reduce this noise content. First thing, and second thing is that this signal, it is too weak. So if we consider, suppose we are sensing some using some antenna, suppose in your mobile handset. So we are sensing some signal of using some your 5G or 4G handset. We are sensing some antenna tower signal. So typically its range it is around minus 40 dBm. Or if you have confusion with this dBm, so in terms of millivolt or microvolt, I can say that it is having some amplitude in the range of some microvolt or millivolt, which is really less as compared to really small as compared to the ripple in the power supply or ripple in the battery or everything. So what we first have to process is that we first have to make this signal. We have first have to process this signal. That is called the processing, and that processing is mostly in analog nature. And for that processing, we have mostly 2-3 things. First is the noise rejection. You have to reject the noise. Second thing is that you have to amplify that. And third thing is that when you digitize it, so there is something called quantization. And there are many more. So another thing is such as if you have some interference. So what are the interference? Interference will mostly come that when suppose you are sensing two attributes. Suppose this is sensor 1 and sensor 2. This is sensor 1 and sensor 2. Suppose the sensor 2 signal is also coming. So these things are so there are the mostly these are the need for the analog processing. And if we go further, okay, sir is also here. Yeah. Okay. So if we go further, then yeah. So mostly our analog signal chain. So now what we have seen that our analog signal chain is mostly comprised of, coming from sensor, we have the analog front end. So this analog front end is mostly comprised of the initial sensing element, sensing circuit, and then the amplifier, and at the end it will just go to the ADC. So this is the most important part of the analog electronics. And for the sensing wise, I can say that the signals are in two formats or in the two domain. One is called voltage mode and another is called current mode. So I'm just giving a very brief of this. So this is little faster. So why this is not going to the next page? So you can you please help me? Okay, okay. This one? Okay, thank you. Yes. So now I am going in detail. So when we are saying that there is something called voltage mode. So normally what we find that one voltage mode signal means we have some signal source. Sorry, we have some signal source which is voltage in nature, and in series with that we have some series resistance. This is called the source resistance. So when you are dealing with this type of signals, to amplify this or whatever do you do, the noise rejection or some ADC, you should consider something that whatever the next stage, the black box you have, whatever it is, this might be on ADC, this might be on amplifier, this might be anything. What it matters is that its input impedance are in. So why it matters for this case? Suppose you have one signal of 10 millivolts and your source resistance is suppose something called 100 ohm, and your R in, it is suppose something called 50 ohm. So your signal, it will your simplified expression, it will something look like this. This is your V in, and then you have some source resistance of 100 ohm, and then you have some input impedance or input resistance. For the timing, I am considering input resistance term only. So input resistance is R in the 50 ohm. So at this node, this is the V in node. This is the V in node. So at this node, and if I call this is the Vs, this is the source. So this V in is becoming Vs into multiplied with 50 by 150. So this becoming Vs by 3. So this is seems like very easy, but this is one real scenario of any circuit, that your input impedance, if it is for the voltage mode of operation, if your input impedance is much lower or comparable, if it not need to be always lower, if it is comparable with your source resistance, this one, what will happen is that whatever the input signal you want at the input of your front end signal acquisition circuit, you will get very lesser amount as compared to the input source. So such as here you can see that my input impedance is half of the source resistance, and we are getting only 1/3 of the signal at the input of my front end circuit to for further processing. So that is the beginning of your analog electronics concept, is that when you are designing, so you should consider that whether you are considering the voltage mode signal or not. If it is voltage mode signal, then whatever the black box you are designing, that whatever I am calling front end, maybe it is amplifier or whatever, its input impedance should be as high as possible. And if you are not able to make it infinite, then you should consider that it is at least much higher than Rs. So what will happen in that case is that my V in, it will be Vs times of my R in divided by R in plus Rs. So this will approximately Vs if this Rs is very less than Rin. So this is one of the required criteria, and you have probably gone through till some course, probably 5 or 6. You are probably more ahead of 5 or 5th or 6th assignment. So there you might found this type of concept, and you might found that there is something called the op amp, and where we are strictly maintaining this thing that input impedance R in is very high. It's going to infinite. So this is the reason why R in should be very high. So now I am coming to the concept of, this is the voltage mode. Now I am coming to the concept of current mode. Sorry, my handwriting is becoming too poor because I am using one pen tab. So now this current mode signal, it is quite different from the op amp, not from the op amp, but quite different from the voltage mode point of view. So suppose I have one current source. This is suppose one current source, and suppose I have the current signal of 1 milliampere, or for your time same thing. So let's like 10 millivolt. It is 10 milliampere, and the current source, as you know, that current source means it is having one Norton equivalent resistance, Rn. I am not going in detail of this Rn Thevenin Norton thing, because probably in some circuit course you have already gone through this, or at the very beginning of this course you have gone through this. So if this is Rn, and suppose this Rn is, again we are considering this is as suppose 10 kilo ohm, not 100 ohm this time, and you are having another front end signal which is sensing this current, and this front end signal is also having some resistance called Rin. So now consider, for the time being, just consider this Rin is also 10 kilo ohm for your time being. So this expression, I am just taking one new page for this one. So then my circuit will looks like this. I have one source resistor, source current. Then I have the Thevenin equivalent Rn or Rs, whatever, 10 kilo ohm, and I have one input impedance which is also 10 kilo ohm and which is taking my current. So my input current I in is, and this is my Is, the source current. So I want that this Is, the 10 milliamps, the most of this should go through this I in. But in reality, what is happening is that if I consider this, then this I in is equals to Is multiplied with opposite impedance by total impedance. So it is becoming half of this. So here you can see the 50% of the input source current is lost in the Rn or in the parallel resistance or in the source resistance 10 kilo ohm, and only 50% is going into the circuit. So in contrary to the voltage mode design, for the current mode design, if you make the Rin as high as possible as compared to the Rn, then you will lose the current. So for this, your Rin should be as low as possible as compared to Rn or as compared to the source resistance. So why this? If your Rin is going to 0, then what will happen? Your Is, sorry, not Is, your I in, it will be Is multiplied with your resistance is opposite resistance Rn divided by Rn plus Rs. So this will tends to Is if my Rin going to 0. So this is another point to be noted, that for the current mode signals, my input impedance should be as low as possible. So in a nutshell, I can just write these two things. One is this for voltage mode. For voltage mode, my R in should be as high as possible as compared to source resistance, and for current mode, my input impedance should be as low as possible as compared to source resistance. So these two are very vital point for any analog designer at the very starting. It should be clear for you. Now next time coming to another point which you might have faced is the some design called, sir, will you take some? No. Okay. So next is, I'm just going to tell about some design concept. So probably most of you have seen that for this is the common emitter configuration, and this is the resistive bias. This is your VCC. Yeah. So for this circuit, so as compared to this one, as compared to this circuit, as compared to this one. So if this beta, suppose this beta is having 150, or and it's suddenly your device got damaged, or you need to replace the beta of this thing, and then what will end with that, suppose you don't have the 150 beta in the market, so you just replace this with 250. So then what will happen, your gain will change. So how this is working is the, not the gain, your operating point will change. So how this is working is that, so if I analyze this circuit, this is V out, this is your RB, this is the RC. So suppose we have designed this for IC, suppose we have designed for 5 milliampere, and your beta is 150. So we have designed this IB as IC by beta, and we consider that VBE is 0.6 volt, and accordingly we choose the RC. Suppose we are taking that this suppose we are taking this as 12 volt, then what will happen? Suppose at the you want the 6 volt here, so you accordingly choose this RC value such as the output will be 6 volt, and the gain you are getting, it is GMRC approximately, obviously it is GMRC, and GMRC means it is IC by VT multiplied with RC. Now suddenly if, what will happen if this beta got changed? If this beta is changed from 150 to 250, then this IB will also change. And if this IB will change, this IC will drop. For this case, the IC will, it will not, yes, this IC will drop. And as a result, what will happen for the fixed RC, your output voltage, it is no more 6 volt. So your operating point got changed. And if your operating point got changed, the IC/RC, because IC is changed, RC is fixed. So your gain is also changed. So this is one of the problem for this type of biasing. So in view of that, what we have used this type of biasing, and this type of biasing is helping us to just let me just delete this thing because it's not visible properly. Okay, fine. So this type of biasing, what we are dealing with, that for this biasing, instead of giving the base current as some fixed voltage, fixed current, we are making the base voltage as fixed, and we are using the resistance such as R emitter resistance, and this is your RC. V out, the 12 volt. So for this case, what will happen? Suppose your beta is 150, and suddenly it changed to the same phase, suppose 250. Then what will happen? Your RE is not changing. Just make a note for this one. Your RE is not changing. First, suppose your RE is 1 kilo for the time being, and suppose you have designed this for this IC, it is approximately the same thing, the 5 milliampere. And for the timing, the V out, we choose the 6 volt. So your and we are considering that alpha is almost going to 1. We are making that IC is approximately IE, and so your IC equal to IE is equal to 5 milliamps, and we need a 6 volt drop here. So that IC/RC equal to 6 volt. So my RC is nothing but 6 by 5 milliampere, whatever it is coming, you just calculate later on. But the point is that what will happen if this beta suddenly change from this 150 to the 250? Then the point is that will the question one is that will this IC got changed? And the question two is that will the gain will change or no? So let's come one by one. So who is deciding this IC? This IC is deciding by the IB, right? But in contrary to that, we just think about who is deciding this IB. So if I take this one as R2 and this one as R1, and if we consider the current flowing through this R1 and R2, it is much higher than, please note this point, this IR1 or R2 it is much higher than IB. If we consider then that this is work here, this is happening, then what will happen is that my VB, the base voltage, is nothing but VBE plus VRE. Now you consider that R1 and R2, these two we are not changing. These two we are not changing. That means this VB we are not changing because of the consideration that IR1 or RR2 is very greater than IB. Now what will happen? This, as this VB is not changing and this VBE, this VB is always becoming 0.6 volt, because from the characteristics curve we know that this is always becoming like 0.6 volt, kind of like this is 0.6 volt. So then what will happen? This VRE, if I fix the RE, then my IE or IC, that is also not changing, that still remain 5 milliampere. So that is the benefit of this design, that whether you use the beta of any value, whether you replace it or during the temperature increase, maybe you are checking, you designed in summer and you are checking in winter, the beta value got changed, so then also it will not matter, that will not matter. And your IC or IE, that current will almost be constant. Why I am saying almost? Because there are some other factors to be noted, but mostly those are almost constant. And now the question comes that will the gain be constant? So what will be the gain of this one? So if you calculate the small signal analysis from search lectures, you can find. So I am not going in detail. So that is almost coming RC by RE. So the gain is little bit reduced as compared to that other previous gain was ICRC by VT. That is quite high as compared to this ICRE. So to overcome this one, what we do? What we do is that at this node, we add one capacitor. So this is one why I just present this this one as a doubt, that what I have noticed that most of the people don't identify that what is the meaning of this capacitor. So if we put the capacitor, so this capacitor, suppose your capacitance is C, so its impedance, it is something like that 1 by j omega C. So for the omega 0 means it is DC. So for omega 0, that capacitor behaves like open because it is infinite impedance. 1 by 0 is infinite, 1 by 0. So now as your frequency is increasing, or your omega, the frequency is increasing, then what will happen? This capacitor is becoming short. And for your target application, if you choose the target frequency in that region where this capacitor is shorted, then what will happen? DC wise, that RE is there, which is deciding this, which is ensuring that this IC is fixed. But AC wise, what will happen? Your circuit, it looks like nothing but this one. Your circuit looks like nothing but this one. So this is shorted. So your gain again becomes quite high as compared to the old one. So this is the normal technique or general practice. We seldom use this type of thing. We normally prefer the left side circuit, this one, because this is more stabilized. And even if you want to replace your transistor or anything happened that beta got changed, then also you can use this thing. So this is another important point. Coming to the next point. Okay. So coming to another point is that what we have noticed in designing, Though this is very at the very earliest stage, I am discussing this one, but this is better to know is that what at the very beginning I told you that input impedance R in. So there is a notion that what people used to say that when they are using MOSFET, this is my RD, my P out, and what is the input impedance of this R in? This is nothing but going to infinite. But and one notion is that people always think like that as the MOSFET is having very high input impedance. So if any circuit, we just apply as some feedback. For feedback, then there is no loading because this Rn is infinite. But the same concept is not true for BJT based circuit. And this is one practical scenario what people used to normally do the mistake that they always consider like that, okay, if I am making the feedback here, so they always consider like that, oh, we can take any resistance value, just we need to consider that whether it is loading this RC or not, and we just give the feedback. But that will not work for this case because okay, just forget about this drawing. There is okay. So what it's a common practice to just use this as a feedback. So I am just omitting the other circuits. There are so many other circuits are there. So whatever the circuits are there, just with respect of that, what we consider that its input impedance is very high. So we generally don't consider this R1 and R2. It is loading with this its input impedance, which is maybe the R pi. Its our input impedance is R pi, and this is quite high as compared to others. And as compared to the it is quite high as compared to very low resistance, but it is not that high as the MOSFET. So for your understanding, I can say that this R pi, it is beta by Gm, and if we for the last circuit, whatever we have seen that for better bias we have used this Re there, then this Rin is becoming in the order of beta plus 1 into Re, which is quite higher as compared to any other value. But the problem is that this never goes to infinite. So this is another aspect which you might face in your designing. So when you are using the off-chip BJTs, so be careful for in the feedback system, you might face this type of issues, or in any consideration, if your sensor output impedance is quite high, then you cannot consider that it's the BJT input impedance is quite high, so we can just directly connect it. So you might need some precautions by increasing the input impedance further, such as you can reduce the that loading effect. So from this loading effect, what I am going to the next point is that, so what is the loading effect it is? So people normally use okay. So the last topic I am going into is the loading effect. So what is the loading effect? What I have shown at the very beginning of this course, of this live session. Suppose you have one source of 600 millivolt, and you are generating this thing, this from any other circuit. Then you have some series resistance of say 1 kilo, and you are driving this one. Use this load. You are driving some load resistance RL, which may vary, suppose from 100 ohm to 10 kilo ohm. Then what will happen is that you can calculate this later. For this 100 ohm, you are getting very lesser signal, only maybe some 10% of the 0.6 volt. And for this one, for 10 kilo ohm, you will get almost close to 0.6. So this is because that my RL, it is coming in the series of this RS and it is reducing at the output. So to overcome this one, to overcome this loading effect, what we use is the op amp. So why to use the op amp before going to that? So my ultimate target is this source resistance. If anyhow we can reduce the source resistance, ideally it is going to 0. If we make the source resistance to 0, then this 10% will become 100%. So for that case, what we can use? We can use an op amp, because op amp output impedance is almost 0. So if we use that op amp is in feedback configuration, in a negative feedback configuration, and if we are considering this 0.6 volt here, forget about its RS, because it is very less as compared to the input impedance of the BJT. So then what will happen? Then what will happen is that whatever the output you are driving, whatever the RL you are driving, irrespective of that value, because my R out it is 0, so you will get exactly same. So your VL, it will be almost same as V in. So this is the one of the trick to avoid the loading effect for voltage mode. So here we are concluding our discussion. So our professor will discuss the later on. Sir, please.
So, hello everybody. So, first of all, I welcome all of you to come to this NPTEL course. I'm sure that you will enjoy and you will get some knowledge about this electronics and specifically analog electronics. So, let me go back to the I should say basic things first, because so far I suppose you have gone through only up to 4 weeks where you have studied about device operations and then also basic amplifier configuration. Now, whenever it comes to, say, analog electronics and the present scenario, it is a lot of digital designs are there. So naturally, your question is that in the era of digital, where the analog is existing and what will be its future down the line. And also, you may be aware that BJT is it was started with, and then later on we do have MOSFET. So which circuit is good and which circuit it will be remaining in future? So these are the confusion you may have. So one is BJT. Versus MOSFET. And another one, it is analog versus digital. So in this course, obviously, we are focusing both BJT and MOS simultaneously. Both the devices are having some pros and cons. Specifically, whenever we talk about why we consider BJT, primarily that is because we consider, say, discrete component-based circuit where MOSFET may not be available. So in case if we are comfortable with BJT, then you will be able to make some onboard design. On the other hand, those people who are looking for VLSI circuit, for them it is important to go to MOSFET. You may also be aware, or at least you have heard, that for analog BJT is good, MOSFET may not be so. So whenever you are talking about analog electronics, then why MOSFET is required? Now, let me answer both of them together. First of all, in the era of digital electronics, we do have a lot of digital operations are there. So we can say it is digital core. And then all the processings and all, it is done in the digital domain. And outside of that, whenever this electronic system is interfacing with the real world, then we do have the analog interface. So the real life, it is analog in nature. And this interface circuit, on the other hand, it is helping us to receive this real signal, converting into a digital form, and a lot of operations are done in the digital domain. And then again, whenever the signal is going back to the real world, it is going through the another circuit, which is converting the digital signal in the form of analog. So you can say that the analog signal it is getting converted into digital by analog and mixed signal circuit. Whereas most of the processing and flexible operations and storing the information, those things are done in the digital domain. So with progress of time, this digital portion, it is growing. And probably this, on the other hand, this peripheral part, it is remaining thin. But then since the number of applications are increasing, so we can say that the scope of the analog design may not be increasing in the same order of digital, but of course it is increasing, and also it will be remaining here. So whenever we are talking about, say, electronic system, on the other hand, so in electronic system, what we do, we process information in electrical domain. And here we give information through something called a signal, and that signal is analog signal. And this signal, I should say not analog, it is the electrical signal. So I should say whenever it comes to the electronic system, it is interfacing with the real world through this analog circuit. And then while it is giving back the information, it is going to analog domain. In between, it is having this code, digital code. So in case if you want to develop a system which is on chip, within a chip, then of course you have to implement the analog circuit and digital circuit together for realizing this electronic system. Now, to realize it, we know that MOSFET is good. for digital. And on the other hand, if I consider for digital, it is of course MOSFET. And then if I consider analog, BJT is better. But then, since the digital portion it is increasing its volume with progress of time, the MOSFET technologies are getting popularized and it is dominating. So in case if you want to realize a system which consists of analog and digital, then the only option it is left behind is that we have to go for a VLSI circuit which is in MOSFET, and then we have to realize analog circuit in MOSFET. So the summary is that even though we can say that BJT is good for analog, but we do have the tendency to, with progress of time, we do have the tendency to make analog in MOSFET, in MOSFET technology. So in this course, we are trying to keep this MOSFET analog circuits along with, of course, the BJTs. So that is one of the reason and one of the important characteristics of this course. We are going side by side with BJT version and MOS versions of analog circuit. The other thing is that why we go for BJT and MOS together, it is there are, of course, there are certain differences, but at the same time, a good amount of similarities are there. So if you know some concept for BJT, you can use those concepts in analog as well. I mean, and in the MOS-based circuit. So, for instance, whenever we'll be using, say, pi model of the device, we are very comfortable of drawing, say, pi model for BJT. Most of the concepts can be utilized for analyzing analog circuit implemented by MOSFET. So since we do have a lot of commonalities, so we prefer to analyze the circuit together. And say, for instance, if I consider BJT, its IV characteristic curve may be something like this. So it may be exponential in nature. So this is the current versus voltage. So for BJT, this relationship, it will be exponential, whereas for MOSFET, it is square law. But still, a good amount of similarities are there. Now, when you talk about, say, collector current as function of collector to emitter voltage, the corresponding characteristic curve, it is almost remaining flat like this, particularly in the active region of operation. So for BJT, MOSFET, similarly, whenever we are plotting the IDS versus VDS characteristic curve, it is quite similar. Though the region of operation, it is stated as a different thing, but its behavior, it is very similar. So of course, a lot of similarities are there. Also, it is having a good amount of mismatches, particularly BJT is current driven or current control. That's how we like to see it is current control device. So its biasing arrangement, it is different. On the other hand, for MOSFET, it is voltage driven or voltage control. So its biasing arrangement is different. So in the course, what we'll be learning is that whatever the similarities are there between these two circuits, we'll be utilizing that. And at the same time, whenever some differences are there, we'll highlight the specific differences. Okay. Now, coming to the other aspect or very simplistic view of an electronic system, as our TA Tamal was mentioning, Thevenin equivalent voltage. Now, let you consider we do have a circuit, and you like to characterize this circuit. Of course, this circuit is powered by supply, maybe VDD or VCC, and so we do have ground on the other hand. And maybe we are stimulating this circuit by some signal, and at the output, we like to see the corresponding effect coming. So to start with, what we'll do, suppose we do not know what is there inside, okay, but we are, as an user of this circuit, we like to see what kind of behavior of this circuit is having, looking at its output. So first thing is that by Thevenin's equivalence model, we can simply represent this circuit in this form. The signal source. So this signal source, it is whatever the voltage you see, voltage you will be observing here. So whatever the voltage you will be observing at this point, before you connect a load, that voltage it is getting represented by this voltage source. We may call it is Thevenin equivalent voltage. This need not be DC voltage, it can be signal also. And in case if you are connecting a load, whatever the changes you like to see, that will be characterized by another parameter called Thevenin equivalent resistance. So this simplification of entire circuit into this form, one is voltage source, another is the resistance. This simplifies the entire circuit in this form. This model, it will be frequently used just to see the utilization of this circuit to connect this block with other circuit. Now, let you imagine that you do have a signal where you like to have a circuit where you are stimulating this circuit by a signal source. Now, so now at the output, whenever you will see, in case if the internal voltage or whatever you call Thevenin equivalent voltage, if it is changing with the stimulus, the stimulus we call it is a Vs, then instead of having different symbol, we'll use different symbol here like diamond shape, and this is our Thevenin equivalent voltage, which may be function of the stimulus. And in case if we are linearizing this dependency of this Thevenin equivalent voltage on the source, then we can think of it as a single parameter called AV times Vs. And in addition to that, of course, we can keep the Thevenin equivalent resistance. So we can model this the output port by these two elements. One is voltage dependent voltage source, and which is Thevenin equivalent voltage, and also this Thevenin equivalent resistance is called output resistance. So this is the model of the output port of the amplifier. Now, whatever the circuit you do have inside this box, magic box, so that part probably it consists of say number of transistors. But interestingly, if you are not really interested about those inner circuit, but you like to utilize this circuit and try to see its signal, which is dependent on the input stimulus, then you can simplistically model this circuit as a linear function of this signal source, which is Thevenin equivalent voltage. And that's why this is the simplistic model of the amplifier. In addition to that, in case if you consider that source is having some resistance, in case source is having some resistance and the voltage coming to the amplifier here may not be same as this one, external stimulus. So this the voltage coming to the amplifier, in case if it is different, particularly whenever the resistance of the source itself is significant. When you say significant, that is in terms of the port loading, input port loading. So which is again characterized by another parameter called input resistance. So the amplifier, now we can model like this. We do have Rin, and then we do have the voltage dependent voltage source, and then we do have the output resistance. So this is what the simplistic model of the amplifier. Now instead of Thevenin equivalent voltage source, we can consider its Norton equivalent, and then we can get the model of transient. So I'm just trying to draw here the another representation of the amplifier. It is something like this, which is a current source, and again this current source may be voltage dependent. So instead of writing, since this is current source, instead of writing or drawing the circuit in this form, we will be preferring to write in Norton equivalent. So I do have the voltage dependent current source, and instead of drawing this output resistance here, I can put a conductance, and its conductance, it is we can call it is G out, which is equal to 1 by R out. And whatever the voltage dependent current source we do have, that can be represented again by a parameter. So we can call this is Norton equivalent current source, which is equal to EM times the input signal, right? And where is that input signal? The signal coming to the amplifier, we call it is the corresponding input. So again, to take care of the loading effect at the input port, we need another parameter called Rin. So in summary, we do have two models of the amplifier. One is this one, and another is this one. And both of them, I should say, equivalent based on your situation. Sometimes we may use the voltage dependent voltage source, sometimes this voltage dependent current. The simple voltage dependent current source we do use for MOS transistor as well as BJT, and typically that's the model which is referred as small signal model. So that is the genesis of linearizing the complicated circuit into simple form, either in Norton equivalent or Thevenin equivalent, which you can think of it as a macro, particularly whenever you like to deal with a big system where you do have multiple units are connected together, maybe cascaded. And for such cases, each of these complex design can be replaced by their corresponding model, equivalent model. And then you can find the the overall gain or overall behavior of the system just by considering their macro model. So whatever we say macro model in this context, probably we can think of it as a macro model of MOS transistor, or we call it is the linearized model of transistor. And those linearized model, it is suppressing the detailed information, but just keeping the essence of the signal part going from one block to another block. So far we have discussed the, I should say, mid-frequency operation or low-frequency operation. In subsequent classes, we will also see what will happen in case if we are connecting a load instead of resistive load, in case if it is capacitive load, what kind of things will happen. Namely, we'll be expecting that R and C, this kind of circuit will be there, which will be its input to output behavior. It will be dependent on frequency, which is referred as frequency response of the circuit. I think that's all we do have. Hope this will supplement some of your information to whatever the lectures are there. And we look forward to see some of the participants directly coming into this forum and having interaction with us. So myself, Pradip Mandal, and also with me, Tamal and Shaikat Sadier from Kharagpur. That's all. Thank you. Bye.